Okay, so I'm going to talk about the applications of complex analysis in relation to Schrodinger's equation in quantum mechanics. So the goals of this video are going to be to describe the motivation for quantum mechanics in general, talk about the double slit experiment and probability waves, talk about the wave function as a complex function, look at Schrodinger's equation and different parts of it, and how the complex numbers are used to derive Schrodinger's equation. So let's get started. All right, so quantum mechanics came about a little over 100 years ago, and it has since replaced classical Newtonian physics as the description of reality. Newtonian physics is basically just an approximation of what happens. It's great for the macro world, but when you get down to the subatomic level, it doesn't work. It falls apart. So quantum mechanics is able to explain interactions of particles at the subatomic level. So quantum mechanics essentially started kind of with this double slit experiment from about around 1800. And you may have witnessed this or may remember this from high school physics as well, or when you see water waves interacting, that they form a kind of interference pattern. And light waves do the same thing. When they interact, they form an interference pattern. And they have these bands of light and dark on the wall where they would end up shining. And this was a really interesting kind of thing that came up, and people would wonder, why does it do that? Shouldn't just, if light was a particle, this photon, shouldn't it just go straight through? After all, that's what experiments with bullets and things like that did. So, but that's not what happens. It creates this interference pattern. So this gave evidence of what was called the wave-particle duality behavior of light. This was that founding concept of quantum mechanics. And the big question was, how can a photon be a particle and a wave at the same time? Well, it was really kind of confusing to people. But numerous experiments since have shown that interference patterns correspond to what's called probability of finding a photon or an electron at a particular location. So that interference pattern actually models what the probability would be of finding it there. So the brighter the area, the more likely you're going to find the particle there. The darker the area, the less likely. And Schrodinger and Bohr, both in the 1920s, hypothesized that light propagated as a probability wave as opposed to a mechanical wave, like electromagnetism might. And so they came up with this idea of the wave function. And the wave function gives all the information about the position of a single particle in 3 dimensions with respect to time. And I've written it out here as this capital psi in 3 dimensions, 3 spatial dimensions with respect to time. And it is an exponential with an I, and k represents the wave number, as it's called. X is position, omega is related to the wavelength, and angular momentum, and t is time. But the problem is, because psi is complex, it can't be measured directly. It's not something you can go and go, oh, I can measure this. No, they need to use different relationships of energy, momentum, and all the other parts that they can measure in order to build the equation for psi. So this first equation here is the momentum, which is equal to h bar times the wave number, and h bar is known as Planck's constant. The energy is Planck's constant times omega, which is also the momentum squared over 2m. That comes from the kinetic energy formula, 1/2 mv squared, which we learned in high school physics. The change in momentum versus the change in the position is proportional to h bar, as is the change in energy and the change in time. This comes from Heisenberg's uncertainty principle, if you're familiar with that. When normalized, which is something we're familiar with, complex conjugates, the square of the norm actually gives that probability density, or some people call it a probability profile of the particle, and it can be graphed similar to this or other types of wave. There's no definite form for a wave function. It can all depend on lots of different things, but it gives this probability profile, as some people call it. So why a complex function? Well, let's look at it this way. If psi was a sine wave, k of x plus or minus omega t, we're going to run into trouble at times when kx equals omega t, or when kx plus omega t equals some odd multiple of pi, sine's going to go to 0 at some of these places, so it can't be a sine function. A similar issue exists for if psi was a cosine function. There are points where the cosine goes to 0, and the wave would disappear, which is, from observation, we know that doesn't happen. So the other option for a wave function is an exponential. An exponential won't vanish for any combination of kx and omega t. It's always going to be something that exists. Even if they go to 0, you're still going to get a wave function. And so for convention, it's chosen the first option here, with the positive I. That's what most scientists will use for the wave function, and they modify it from there. Notice that there's that lovely exponential with an I that we're all familiar with now. Additionally, if you come from the aspect of the Schrodinger equation, psi must be complex for this equality to hold. If psi was a real function as opposed to a complex function, then the right side would be real, and this I here, the complex I, wouldn't work. It wouldn't work with the right side. So to make this work, it has to be a complex function. Otherwise, the Schrodinger equation itself would just not work. So it's almost forced to be, if you look at it from that perspective. Again, a probability profile is when norm squared, psi gives the profile of probability distribution of the particle's location. And here are some equations to calculate that probability. Again, it's dealing with the norm squaring, multiplying the function times its conjugate. And if you're familiar with probability, of course, the total probability has to equal 1. So that's just the integral there, the infinite integral there. Okay, and now we'll get to the Schrodinger equation. This is the quantum mechanical analog of F equals ma, which is Newton's second law of motion. And at the macro world, F equals ma works just fine. It works great for sending rockets to Mars. But at the micro level, at the subatomic level, it doesn't. So the Schrodinger equation is basically the F equals ma of the quantum realm, quantum world. So beginning with the generic wave function and using these relationships of momentum, the wave number, energy, and omega, and that, we can derive the Schrodinger's equation. So let's start by taking the position derivative. Okay, and because it's an exponential, we just get the ik times the equation times the function back again, which is pretty nice. It doesn't change it. And using the relations up above, if we modify it a little bit, if we multiply both sides by h bar over I, again, h bar is Planck's constant, h bar over I, we can come up with that h bar over I times the first position derivative is equal to the momentum times the function. So this is an equation that describes the particle's momentum. We can also take the time derivative, and we get a similar equation for energy. Right? By multiplying by I h bar, we get an equation for energy. Again, using these well-known basic physics relations up here. Okay? By comparing the two equations, relating them together, and using a little bit of algebra, it's not too difficult to follow this. Doing a little bit of algebra, we can come up with the fact that I h bar times the first time derivative is equal to negative h bar squared over 2m times the second position derivative. There's the acceleration idea right there. And this is the basic kind of form of the Schrodinger equation for a single particle in maybe one dimension. It gets a little more complicated when you expand it to 3 dimensions. But that's by basically just using that. And you can't be done without that I. So it's an interesting form of using complex numbers, and it's a little bit of algebra there. All right, and of course we know again from basic physics that total energy equals kinetic energy plus potential, or it's also called an external energy too, and anything from the outside. So the full Schrodinger equation for a single particle in maybe one dimension, because I don't have any vectors listed on here, would be something like this. You've got the V represents the potential, again, times the wave function. And the general solution of the wave function can be found in this way, where you have this function phi of k, again, of the wave number. And omega is also dependent on k as well. So that's would be the general solution of that. And there's many different ways to work through this, depending on what type of particle, the speed, all the different things. But in order to analyze a particle, you need a complex function. Whew, all different forms of it. All right. Thank you.